you see the main slide, correct?
Yep. Yes, correct.
Yep.
Okay, very good. Okay, yeah. So yeah, thanks for inviting. So I'm not 100% sure like what was the required format of the presentation. So I try to like put a few things together. So this is also some little bit generic information about my field and also more information on specific projects. And at the end, I just give you an example of one of the projects which we recently had. But essentially what we do here is we work with superconducting circuits and we try to control and measure them at quantum level. Okay, but before I proceed, so I probably make sense to introduce myself and just give you an idea of my background. So I got my PhD in Clarkson University in USA. So that was on essentially fundamentals of quantum information theory and also a little bit about theory of solid state qubits, like decoherence, etc. So after my PhD, I got my first postdoc in Germany. This is Karlsruhe Institute of Technology. And this is actually, it was an important step because I started to work theoretically on superconducting quantum devices. So this is the time when I actually learned for the first time how it works in theory. So I was so taken by that I decided that it would be much more fun to do it not in theory, but in practice as well. And therefore I switched to like an experiment. So I went to TU Delft. So this is a famous quantum transport group. So currently it's a QTech Institute, which I don't know, maybe you heard about it in Delft, which started after I left already. And so this is one of these experimental groups which started superconducting qubits, and in particular, they invented the flux qubit. And during my time, I developed a particular version of the flux qubit, which is called the tunable gap flux qubit. So after that, I went to ETH Zurich, and in ETH Zurich, I started to work more on quantum protocols. So in particular, I was the first to demonstrate a 3-qubit gate with superconducting qubits, and also the first quantum teleportation in any solid state systems. So that was like 2 big projects in my time there. So after that, I looked for a permanent position and applied at UQ and got a position and appeared here in 2013, which is almost 10 years, yeah, that's 11 years ago, right? And I founded a new laboratory, and I'm the head of the superconducting quantum devices laboratory. So just to give you an idea, I've been chief investigator on ISC Center of Excellence for Engineered Quantum Systems. There were 2 centers, the first one and now second one at its end. I also got future fellow at some point, fellowship at some point, some UQ Research Excellence Award 2 years later. And one of the big things, recent things for me is that 1 year ago, we found, I co-found analog quantum circuit, which is, okay, we like to call it the first quantum tech startup in Queensland. Also, if you have any questions, please feel free to interrupt me at any point. Okay, so like as a very generic introduction, so we have different quantum systems which are good for quantum technologies. And here I just bring you some examples of platforms which are developed in UQ. And of course, traditionally, the natural systems like photon and atoms are the system which showed like quantum dynamics, and historically the first. So this is not surprising because we all know that quantum systems like atoms are, I mean, by definition, quantum. But later on, there were 2 like different systems, which often are called artificial systems. And this is like one of examples of that is an optomechanical device, or even superconducting quantum devices, which is probably the most artificial systems of all. So why artificial systems and what is better about artificial systems? Why we are not happy just with the natural ones? I think there are, of course, pros and cons for all platforms. And generally, natural systems are cleaner. So, for example, if you take a single atom, it's very, very good qubit, and it's very, very clean, and has a long coherent times. But on the other hand, the parameters are typically fixed. It cannot be tuned, and often it's hard to couple this clean system to each other because they're very isolated, very well isolated from environment. So in contrast, the disadvantage of natural system become advantage for superconducting circuits. So superconducting circuits are designed, right? So therefore parameters can be designed already before the experiments. And many of these parameters can be even tuned in situ in a very large range during experiments. So this is a kind of a strong point of superconducting circuits. But because, of course, they are fabricated and they are still solid-state devices, they are relatively dirty. So their coherent times are never as good, although they're very good still. They are never as good in absolute terms compared to the natural systems like spin or atom. So because I didn't know exactly how much you know about quantum circuits, I decided I give you a little bit of introduction. So, and before I talk about quantum circuits, let's talk about conventional circuits. So what are conventional circuits? The simplest linear circuits are capacitor, resistor, and inductor, right? So they can be described by voltages, charges, fluxes, and currents. And if we add a nonlinear element like a transistor, we can create a very complicated modern electronics, such as shown on this picture, like some processors and semiconductor technology. And I think the fact that we have this nonlinear system gives us this functionality. So if you didn't have this like a transistor, so of course there would be no computational power as we know. In quantum regime, we can also think of linear circuits, and that would be the same capacitor and inductor, but not the resistor, because we all know that resistor will kill quantum correlations. So resistors are not allowed. And if we would like to build the simplest quantum circuit out of circuit elements, that would be LC oscillator. So we can again introduce, for example, fluxes and charges. We can write down the classical Hamiltonian. Then we can quantize our system and replace these variables with operators. And then these operators will be conjugated, right, as a coordinate, let's say generalized coordinate and generalized momentum. And therefore, we have to impose the corresponding computational relation between these operators. And of course, we all know how to solve this Hamiltonian. So this Hamiltonian is the same as Hamiltonian of a harmonic oscillator. So one way to find its eigenvalues is to introduce creation and annihilation operators, right? And therefore, the eigenstates will be number of excitation in the circuit. So the minimal energy will be the ground state energy. There will be zero excitation, and then there will be, we add another photon of energy or quanta of energy, and then we will have all other energy states of this system. So this is a quantum system. So it is important to remember that each of these states, which are Fock states or number states, they don't have a counterpart in classical mechanics. However, a problem with this system is that it cannot be used as a qubit, but rather than a microwave photon. And the problem is that it's very hard to isolate, let's say, two logical states out of infinite states. And this is because the spectrum is harmonic, right? So if you try to excite our system from a ground state, we always excite all others. So that means that we need, and similar to classical electronics, we need some nonlinear element, because otherwise we actually cannot use, let's say, quantum mechanics in full. So linear circuits, although they are quantum mechanical, will be of very limited functionality. But the problem is that most of electronic circuits, if they are nonlinear, they also are quite highly dissipative, and they have lots of resistance. So in some sense, that looks like a counterative requirements, right? So we want nonlinearity, but without dissipation. But fortunately, superconductivity gives us a solution even in this case. So the element which I show here is the Josephson junction. So Josephson junction is just two superconducting electrodes separated by a very thin oxide layer. So the peculiarity of this element is that this oxide layer is quite thin. So actually, you can use transmitting electron microscope picture to have a cross section through the tunnel junction, and you can actually count number of atomic layers in the insulating barrier. So this is really very thin. And because it's very thin, the Kuiper pairs, which are charge carriers in superconductor, they can actually go through this tunnel, through this barrier, and create a current, which is a supercurrent, and can flow without resistance. And of course, this is described by famous Josephson relation. So, for example, current is proportional to critical current times sign of phase drop of superconductor over the Josephson junction. So that has very rich dynamics and physics, but the simplest view on the Josephson junction is that it is inductance, but the inductance which will non-linearly depend on the current through it. So this is exactly what we need. So this is an inductance, which is a non-linear. So its response is essentially non-linear, but resistance, which I show here, is essentially negligible. So you can, by all means, say that it's almost non-dissipative. So if you use then this element, so then we reduce the transistor with the Josephson junction and of course remove resistor. We can create an enharmonic oscillator. And in this case, you will see that the spectrum of the system will be enharmonic. And this is an analog of electronic artificial atoms. So in this case, the spectrum will be like all the transition elements will be different. And this is very similar to the spectrum of an atom. Indeed, the simplest qubit which currently is used and the most common is called Transmon qubit. It's nothing less as a nonlinear oscillator. So the two lower states are used to encode quantum information. We can call it as 0 and 1. And sometimes we also use the second excited state. So the difference between transition frequency is about 300 megahertz. So this is smaller relative to the transition frequency, but it's still much higher than the line width of our level. So we can still address these transitions individually without, so if you address 0-1 transition, so the 1-2 transition will not be excited. So therefore we can use this as a qubit, and we can have all the control of a single qubit. So for example, if you apply the oscillating charge or voltage through the coupling capacitor, we can induce transitions. And if we have, instead of a single junction, a squid loop, two junctions in a loop, we can also tune the frequency of the qubit by applying magnetic flux in the loop. So here I show you like an example how Transmon frequency changes with the flux bias. So that sounds quite simple, but I mean, is it simple in reality? And of course, some time ago, people thought it is even not just simple, but even impossible, like a science fiction. But of course, at the moment, we know the tricks, and essentially, in the simplest term, the recipe is as follows. So we have to avoid dissipation as much as possible, and for that purpose, we use superconductivity. We need to cool it down to very low temperature so that we initialize it in the ground state. So for that, we put it in the dilution fridge. And of course, because we still have to connect it to the outside world, right? Because we need to control it and read it out. We also need to be quite clever about filtering the noise coming from room temperature electronics. And if you can do that, then essentially it should work. And Indeed, it works, and it almost at every scale we have our solution. So we have at the very smallest atomic scale, we have our tunnel barrier, Johnson junction, which is the smallest element. So this is much bigger. This is a fraction of a millimeter. This is a superconducting qubit, a Transmon qubit, which we can fabricate. No, sorry, I'm on a call. Yeah. Then we can put a chip in a sample holder. And then we can package it and connect to the circuitry, and finally mount it into the dilution refrigerator. So essentially, that's the main elements which we have to work in our lab. Okay, do you have any questions so far, by chance? No. Is it like too elementary to fine? Okay, let's proceed. So here I would like to talk about circuit quantum electrodynamics, or circuit QED in short, because this is the most common regime which is used for experiments with these systems. So circuit quantum electrodynamics came about or came after cavity quantum electrodynamics, and cavity quantum electrodynamics is a term from quantum optics. Oh, sorry. So people some decades ago who studied quantum optics, they of course tried to see quantum effects. And of course, if you have like a single atom in a free space, the probability of a photon to scatter around atom will be quite small. So therefore, people thought that if you put it inside a cavity, then you sort of enhance this interaction, and then the system is described as J Cummings Hamiltonian. So if your coupling strength will be greater than dissipation losses, then you can actually observe the coherent exchange of excitation between an atom and the cavity. So this was kind of a holy grail of quantum optics for decades. So in circuits, you can also use a cavity. It can be, for example, a Kaplana waveguide cavity. So it's a Kaplana waveguide where you can put, instead of mirrors, some capacitors. So there will be standing waves here. Then you can put a Transmon qubit. And because Transmon qubit has enormous dipole moment, then the strong interaction regime is very easy to achieve. So we can always increase the dipole moment so that we have the interaction strength much larger than all the dissipation channels. So this is a piece of cake in our case. So this was very popular, and essentially in almost all experiments, this kind of strong interaction plays a role to some extent. And I just would like to give you a little bit of flavor of what kind of experiments people do. So first of all, people, because I already started from quantum optics, then it's clear that you can do quantum optics experiments, but with microwaves. So this is quite all result where people use their, let's say, superposition for Fock states in the cavity by use of a qubit. Then people also created CAD states for microwave photons. And in a similar way, people use qubits, superconducting qubits, to control other bosonic modes. So here in the first two experiments, these bosonic modes are cavity modes. But in principle, people also can use to create various quantum states for phononics, for phonons, and for essentially magnons and all other bosonic modes. So one first application of circuit QED is using qubits as a tool to quantum control of quantized bosonic modes and do things which people would never think possible, like these CAD states or like a complicated entangled states. And now people do even more complicated states like for error correction, etc. An interesting thing, though, which I would like to say that we don't need to have a cavity. We can, in principle, remove and go back to open space. We can remove these mirrors. And because it's 1D system and qubit has a very large dipole moment, we can still have a very interesting situation and very like a situation which is very hard to engineer otherwise in 3D space. So, for example, if you shine microwave coherent tone onto our Transmon, Transmon will have a dipole moment which will radiate like in both directions, and that interferes with the incoming wave in such a way that essentially all the radiation will be reflected. And for example, if we, so that's one of the pictures which we got with one of the Transmon qubits, and you see that it's we have a suppression of transmission more than 40 dB. So that means that more than 0.01 photon only get transmitted, and 99.99% of photons are reflected. So this is, if you compare it to actual real atoms in 3D, then the record is about 10%. So this is very, very like more advanced platform. And this is exactly because the coupling is strong, and therefore the radiative decay is much stronger compared to all other decay channels. I would like also to say that in the first experiment where people showed it, they showed 99% reflectance. So we can put many qubits in these waveguides, and that would create even more interesting physics. We can have like long-range qubit-qubit interaction, and we can also have some super and subradians. And this is interesting for quantum networking, because in this case we have we are not constrained by the cavity size, and it also can be used for non-reciprocal devices. So because it's now, we don't have a quantized mode, but we have a continuum in open 1D space that is called not a circuit QED, but waveguide QED regime. So this waveguide QED regime is a little bit perhaps less developed as circuit QED regime, but has more novel physics at the moment.
Have you shown super radiance in your system?
Indirectly to, yeah, like for example, we showed that the lifetime of 2 qubits for some states, there are some subradiance and super radiant state. Like in this paper, which is the first paper where we like anyone observed more than one quantum emitter. So that was in 2013 published. It's in my experiment. So we only had 2 qubits, and we only showed that that there is a plus state has a twice larger decay rate, and minus state is a dark state. So there are some other experiments on superradiance and subradiance, where some aspects of that is has been demonstrated, but I don't think everything has been demonstrated. So of course I know that it has to do with quantum batteries. Has some relation. But more interestingly, recently you can do even more so. So instead of let's say removing these mirrors, you can actually put modulation of your medium. So in this case, it's something in between. It's not a quantized mode and it's not a continuum, but that's, of course, as we know, it has some bands, stop bands and phase bands. And here you have even more weird and interesting physics, and that has to do with atom photon bound states, topological edge states, some interesting novel spin models, etc. So we also work a little bit in this field as well. But of course, so those applications are still more like exotic applications if you compare them to quantum computing, because of course quantum computing, when it started in, let's say, superconducting qubit history started in 1999 by a charge qubit, which showed the coherent times of about 1 nanosecond, right? And you could see a few coherent oscillations. And right now, okay, in 2020, you have 20 or 100 or hundreds of qubits, and coherent times exceeding hundreds of microseconds, and fidelities of operations well beyond 99% for 2 qubit gates, and even more so for single qubit gates. I think right now there are many quantum computers already, but they're still, I would say, like a toy quantum computers, so they're still not practical yet. But depending on the forecast, depending on the people would say that it can become practical within, I don't know, 5-10 years from now. Okay, so from now I finished like kind of an introduction, and I would like to give you some list of what projects we do in our lab. Yeah, so recently we work quite a lot on non-reciprocal devices, microwave devices. We try to use quantum effects to induce non-reciprocity for some circuit on a chip. So in particular, like in 2008, we demonstrated the first non-reciprocal microwave devices where non-reciprocity was induced by quantum nonlinearity. And more recently, we started to work on a passive circulator on a chip. And this is the project which essentially gave birth to our startup company. So this is our goal. And we are currently working hard on actually creating a circulator on a chip, which is also not just a proof of principle, but a practical device. But it's not yet, of course, finished, still in progress. Yeah, then we work on a waveguide QED and with a band gap. So it's still ongoing. So we studied bound states in the stop band. And recently, we theoretically proposed some directional edge states, which can be used for coupling of qubits and so on. And so that was a theory proposal, but we are currently working on the experimental implementation of that. So this is another branch of our research. So we also work quite a bit on fabrication of our devices. So although superconductors, of course, have little dissipation, so still dissipation, unfortunately, is not removed completely and never be possible to remove completely. So we also have a linkage grant, which recently started together with IQM, quantum computing startup, where we aim to improve surface losses of these devices. And another project which is going on is to use phonon engineering for superconducting qubits. And one kind of application of that is to protecting qubits from quasi-particles which are generated by cosmic rays. And finally, probably still the biggest activity is still about control and measurement. So we use, of course, we cannot do quantum protocols, cutting-edge quantum protocols, because so this is an activity for big companies like Google, IBM. But we still use lots of tricks to improve one of two aspects of quantum computing. So in particular, we had some work on how to use qubit for as a probe. So in one instance, it's a probe of signal, control signal, so that we can measure control distortions in situ and then correct them. So also measure temperature or non-Markovian noise. So we had some, let's say, work related to quantum measurement, how to on-demand protect some of the qubits from back action, or how to improve fidelity with neural networks. And recently we have more fundamental project which is related to quantum clocks. So we try to implement clocks with superconducting circuits and see what are the limitations of quantum mechanics on timekeeping. And if I have time, so in last maybe 5 minutes, I would like to show you one of the examples of our measurements. Do I have time or not?
Yes, you do. Yes, you do.
And I decided I chose one experiment, and this experiment is how we measure temperature. Because I also know that James also has some ideas. I actually have no idea what how you're going to measure temperature, but that's what we did in our lab some time ago. And we did it with our particular way, which we developed, which has some advantages, and I will describe it. Yeah, so we still, the main motivation for us was still quantum computing. So these are requirements for quantum computing. And one of the requirements is that we need to initialize qubit. And typically, qubit is initialized in the ground state, and often by just cooling into the temperature of the dilution cryostat. However, people often observe some spurious excitation of the qubit, and of course that would create first initialization errors. But secondly, that also gives you some indication that your qubit is coupled to some environment which has higher temperature, and often can lead to some kind of insight into decoherence, which is also necessary to improve for our quantum gate. So if you take, let's say, the transition frequency of Transmon, let's say 7 gigahertz, and then you take the base temperature of cryostat, which is, let's say, 20 millikelvin. If you calculated the expected population of the excited state for Maxwell-Boltzmann distribution, you'll find out that it will be, of course, very, very small. So it will be like very, very like a 10 to the power minus 7, 10 to the power minus 5. However, almost in all experiments, what we measure, we typically measure the spurious excitation of the order of up to 1%, or even a few percent, or a fraction of 1%. So although it is quite small, it is actually orders of magnitude larger than what you expect if your qubit was thermalized. Yeah, as I said, it's important for initialization errors, and also we'll show you that we have some decoherence channel. And the problem with this measurement is that although it's much larger than expected, it's still quite kind of small. So therefore, it is relatively hard to measure with high accuracy. So currently, there are two main ways to measure this excitation. And the first one is to use, let's say, high signal-to-noise ratio readout, for example, to use those parametric amplifiers. So in this case, you typically can count directly how many excitations you have. So basically, you prepare your qubit in the ground state, right? And then you measure it, and then you just repeat many, many times. And sometimes you actually see that sometimes you have, let's say, the response is on the wrong side. So that means that the qubit was excited. So in this case, you can actually directly see how many times you have excited qubit out of all measurements. But that requires high signal-to-noise ratio, which is not always available. So another one is to use the high excited state. So the second state, like second excited state, which I showed you. So for example, if you have, if you try to, let's say, induce Rabi oscillation between the ground and excited state, you will see like high visibility oscillations. But if you try to do Rabi oscillation on a second transition, you will also see some visibility. And as far as you see visibility, that means that you have some excited states. And by compare ratio of these visibilities, you can actually deduce the actual excitation probability. So that works as well, but that only works if you have a high excited state, which is not always the case. For example, for some of the qubits, you don't have this transition available. So what we used is a completely different scheme. So this scheme depends on the correlation, measuring correlation between two measurements. So suppose you measure one time the qubit, then you have some response, some average, let's say, outcome, which will be proportional to responses in the ground state and responses in the excited states, and then times their probabilities. So if you apply a second excitation, then you will see the first order correlation function, which will be proportional to this thing. And if you then take these measurements apart very far away, then your correlation will be, so the measurement will be completely uncorrelated, and therefore you can approximate it by another expression. So by using these three expressions, you can actually, by measuring these three values, so actually the single measurement M1, then the correlation function at 0 and correlation function infinity, you can actually then mathematically extract the excitation probability. So indeed, just to try to demonstrate this, the same thing with let's say some measurement. So like here we actually measured the correlation function, a function of time between pulses, and indeed you see that it's a decaying function, and the decay time is essentially the relaxation time of the qubit T1. And indeed you can see that the amplitude of this decay is actually the bigger the higher the temperature. So that already tells you that, yeah, indeed, probably that has this information of the excited state of the qubit. So then that's exactly what we did, and then we did it just more carefully. So we did it like for our method with parametric amplifier, and this is the top picture. And then we did it as a function of mixing chamber temperature, which we just controlled just to see if, I mean, how our measurement responds to it. So we see that, okay, of course, with higher temperature, the expected excitation grows, but at some point it saturates and stays at some level below 1%, which is 0.33%. And we see that the arrow bars are all very small, essentially almost minimal. So we managed to measure it with an accuracy that's less than 0.01%. So wow. This is the most accurate measurement I aware of, which measured the excitation probability of a qubit. Of course, if we remove the parametric amplifier, which is just higher, which increase your signal to noise ratio, then yeah, we get essentially the same measurement, but the arrow bars become bigger. So we can also compare directly this parametric amplifier by counting without. So it's consistent, but the arrow bars still in our measurement is still better. And we also use the Qutrit. So Qutrit actually the least accurate method because it includes lots of, let's say, population, like driving. You have to be on resonance. So you basically, there are more things to calibrate. So one of the questions is, what is this? So why our qubit is excited? Yeah, obviously it has to be coupled to some bath with high temperature, and most probably this bath is actually hot quasi-particles. So why is that? So this is because we can use our method to do so-called a temperature spectroscopy. So we measure this excited state population of the qubit versus the frequency of the qubit. And then we see that, so the measurement which I showed on the previous slide is shown here by the green line. So it was at 6.25 gigahertz. But we see that the excited state probability is actually a non-monotonic function of the qubit frequency. So for any models, yeah, you would expect that would be monotonic. So it means that at some frequency, in some specific frequencies, we have some high excitation, and then actually that points towards two-level systems. So this is a very characteristic behavior for two-level systems. But most probably two-level systems have to be hot, and they are hot because they interact with hot quasi-particles. So this is our current theory behind this behavior. But in order to disprove or prove it or get more information, of course, more measurements is necessary. Okay, so essentially, I would like to finish right now with this. And okay, in principle, if you want to have a look at our lab and even our devices, you can have a 3D tour. So you can go to our website and click, and then actually walk in our lab and see what we have there. So I think that's it.
All right, excuse me. I have a question.
Mm-hmm. Yeah, go for it.
It's okay. Then my question is, and capability for fabrication of quantum chips, and your company and analog quantum circuit company and have a fabrication equipment including lithography.
Okay, analog quantum circuits is a startup, so we currently like 2, 3, 4, like 5 people. Of course, we don't have any fabrication equipment. Yeah, because fabrication equipment is it's expensive, right? So
yeah, I know.
it completely doesn't make sense for a small startup to have. We even don't have a dilution refrigerator. So currently, but we fabricate chips at UQ on campus. So there is the INFF node and also Center for Microscopy Microanalysis, which have electron beam lithography. And also my lab, we have our own electron beam evaporator. So
okay, good.
So this is what we use. At our scale, it completely doesn't make sense to have our own fabrication.
Okay. Then how about design rule and on your current device, Ryan and space?
So what about design?
Yeah.
No, what is the question about design?
Yeah, and this question is and the 2 items. And the first one, okay, and capability of and the Ryan and space and probably submicron. How about and the design rule on the chip?
So what is the size of our devices? Or
yeah, on device.
Yeah, that depends on. I mean, different devices have different sizes. So Transmon has a footprint of hundreds of microns. So the smallest feature of our devices is Josephson junction. This is hundreds of nanometers.
Okay.
But a superconducting qubit, it has big capacitor plates, so it is hundreds of microns.
Okay.
But some of our devices, for example, the circulator which we designed, it's tens of microns, so it's smaller than a qubit, but I mean it's not nanometer. So our smallest feature is sub-nanometer, but it's only smallest feature. But the circuit itself is typically micron or tens of microns or even hundreds of microns.
Okay. And sorry, and the final question, okay? And do you have any, circuit design software?
Circuit designs of?
Yeah, then like a SPICE and software for
software.
analog circuit.
You mean for simulation or for designing?
Yeah, simulation on the computer. Yeah. Yeah, sorry. Sorry. In my understanding, okay, and we can, make a, circuit design and the simulation software on the computer and for a normal silicon chip, but not include the superconducting phenomena. Okay, then my question, and do you have, okay, and circuit design software including and the simulation, including superconducting and the devices?
No, we don't. So far, we use the same designs for just normal, let's say, CAMSOL. Recently, we use PALAS, but all of them don't include superconductivity. So it would be nice if you can, but yeah. So there are some design softwares which has some physics, some superconductivity physics, but they're not as advanced in other areas. So therefore, we don't use them.
Okay, it's still issue. All right.
Yeah, still issue. Yeah, if you can produce such a thing, would be great.
yeah. I think so.
We can use it, but I mean, obviously, we don't have manpower to to work like closely on let's say our own simulation package. So we typically use something which is well, we use either COMSOL or ANSYS, HFSS, or recently we used Pallas, but none of them include superconductivity in a proper way, I would say.
Okay.
So yeah, so thanks for that presentation. That was really fantastic, and there's I think we're going to have a lot to chat. I have to leave at 5:30, but I'm going to make a few comments and questions, and anyone can put up your hand to have a question or comment or just to jump in. But I'm just going to go because normally I don't rush because I have time, but today I have to catch a flight, so I can't be too late. So Hirai-san, I think that's a really good idea. So potentially we could do maybe have a project where we extend the software, or write software which will include superconducting properties. I think that would be really useful. That's something we could talk about, Hirai-san.
It will be useful. Yeah. It will be useful not only for us. I think it would be generally very useful in the worldwide.
Yeah. Because I know Hirai-san has been doing simulation with other circuit fabrication material software, but nothing with superconducting, so that would be really useful. I'm just gonna make a note of that. Okay, so I actually have a lot of things to say, but I'll just sort of limit to some of the few things. So your work on temperature measurement using superconductors. As you know, we put in a grant to do quantum thermometry, which was successful. And now that I've seen your presentation, a lot of your work shows that the requirement that we need is actually really feasible. So the difference between what you've done and sort of what the proposal that we put in is that we want to look at the time like UNRWA temperature, and the only difference really is that we need to have a tunable energy gap. So we want to accelerate the energy gap, and according to essentially Tim Ralph's theory, he was the first one to come up with this, that will produce a thermal response, which essentially is the UNRWA temperature. And what we showed as a case study in our paper is that we only need to measure the excited state population to about 0.1% accuracy, and I think you've achieved something much more than that, right?
Yeah. Yes. Yeah. 10 times better.
10 times better. The only difference, also the other difference, is that we need a three-level lambda system, and so we propose a fluxonium design. I think you've worked at fluxonium 3-level systems before. Is that right?
I mean, not so much. No, I have not worked with fluxonium. We fabricated it once for fun for a student. So like honor student fabricated it, but actually we have not even measured. I mean, we measured spectroscopy, but I never controlled it. But I mean, this is just another qubit for me.
Yeah, exactly. In the end of the day, all we need is a 3-level lambda system, which is tunable, which can measure. But the tunability gap, we need, what we calculated was we needed something like changing the gap from 1 to 10 gigahertz. Is that achievable with your system?
I mean, but you shouldn't. I mean, which system are you talking about? So we use Transmon qubit, right? So basically, if it's necessary, I mean, there is no like. I mean, we do system relative to requirements.
Right. Yeah.
If we need this, then we can choose like, for example, fluxonium and create fluxonium. Fluxonium can have a small gap, like much smaller than it can be even less than gigahertz. Like for Transmon is not typical to work at this low frequency, although it's still possible. Because at 1 gigahertz you start to thermally excite it, so therefore typically people don't work at these frequencies. But let's say if it's flux qubit, I had a flux qubit. I have a paper long time ago, 15 years ago, where I operated flux qubit up to 100 megahertz. So the qubit frequency was changing from 100 megahertz to gigahertz.
Yeah. So in your presentation, you talk about these quasi hot particles. Well, what are these quasi hot particles?
Quasi-particles are basically, you can think of them as electrons. So there is a Kuiper pair, right, in superconductor.
Yeah.
So if you break a Kuiper pair, you create two quasi-particles. So, but the quasi-particle states are separated by a gap, superconducting gap. So this is why you have superconductivity. Because if your temperature is lower than the gap, then in principle you are not supposed to have this quasi-particle. Yeah. So if you, in a similar way, if you assume that your superconductor has a temperature, which is, for example, 20 millikelvin, and for aluminum, the superconducting gap is 1.2 Kelvin. So then you can calculate the Boltzmann probability to excite the next excited state, which is called quasi-particle, but effectively this is just you have to break a Kuiper pair in two electrons. Then you will see that there will be no energy to excite it. So there would be the natural density of quasi-particles has to be very, very small. It's exponentially suppressed. But in reality, it's not as small. And like one sources of that would be this cosmic rays. So the cosmic rays, they would hit substrate and release lots of phonons. And these high energy phonons, they would reach superconductor and break Kuiper pairs and create quasi-particles. So therefore, people call these quasi-particles non-equilibrium quasi-particles. It's not 100% clear what sometimes where they come from. But quasi-particles are electrons. Once you break a Kuiper pair, you create electrons, which are called quasi-particles.
Got it. Understood. So I'll probably arrange a meeting early next year about the Quantum project with Tim Ralph and Bill Monroe and a lady called Gia Du here as well. So it's the other. So I'm talking quickly because I need to explain. But the other project was the quantum battery project. So that's so that's moving ahead. So that's we're going to have as you know, we're going to have a postdoc with you in UQ. So that's sort of moving ahead. So things move a little bit slowly here at CSIRO sometimes. And the other postdoc will be a theoretician, and of course Ksenia, which I was hoping to talk to you about today because there's a few things that I need from her through you. I sent you an email today. Is the information okay to get for that?
Yes. Yeah. I sent that request to her because I also don't have this information, right?
Yeah. Yeah. So we'll get that. I'll probably again probably early in next year we'll have a meeting about that. And the other project is the one with Seth and Fakar here on using single qubit quantum machine learning algorithm. And I was hoping to have time to talk to Seth and Fakar about it today as well, because I know that you guys are trying to arrange to get together to demonstrate the quantum robotic quantum robotics with quantum machine learning using the classical computer in quantum and so after that, yeah, we'll want to use the actual single qubit for the quantum layer of the neural network hybrid model, and so we'll probably use your system, or we will use your system, and hopefully by then I will have that postdoc working with you, Arkady, to help do that. The other thing I wanted to mention was so Kareem. I know, Kareem, did you want to say it now? I'm sorry, I'm rushing. I have to leave, but
sorry, no, you're all good. I was meant to present next Monday, but I might not be able to attend the meeting. So if I could swap my presentation with someone else's for some time in future, if that would be okay.
So who was meant to be next after Kareem? I can't remember. Kieran knows.
So we had another guest after Kareem.
Yeah.
But give me 2 seconds.
And would that be beginning of next year, or is there another meeting before the end of the year?
There's another one before the end of next year, but
yeah. So After Kareem is supposed to be Sabrina, and after Sabrina, Jack.
Okay, Jack, can you swap with Kareem? Is that all right? Or for next week? Or is that too early?
For next week?
Yeah.
Sure, I can send some measurements, I suppose.
Yep.
That I have not gotten yet.
Yeah, that's fine. That's fine. Actually, so the other thing I forgot to mention is that we also like to have the slides accompanying the video. Are you okay to send your slides to us, to Kieran?
Mm-hmm.
Yeah. Okay, that'd be great. Yeah. So I know I've got a minute left, but I'll open the floor. Questions, comments. Yeah, go on, Kieran.
Can I just ask a quick question? So first of all, Arkady, it was a wonderful talk. I learned a lot in such a short space of time, so really cool. And the quantum thermometry measurements also very impressive. So my question pertains to that system, and maybe it's a bit sci-fi, but you tell me. Is there the potential to couple these Transmon qubits to a sort of semi-arbitrary system and measure the temperature of that system rather than the temperature inherent to the qubit? So you're using it really as a thermometer to probe local environments.
Yeah. Okay. So that's. I mean, of course, in principle, yes, but that's actually the whole point, right? So the thing is that. The whole point is that the qubit, although like you put it in the fridge, right, and you know the thermometer in the fridge, and it shows you, let's say, 20 millikelvin. But you measure the temperature of the qubit is actually a different temperature because qubit is coupled to some other. Qubit is coupled to many many environments, and this environment, which is 20 millikelvin, is just it's phononic environment. This is like actual. But at the same time, there could be some, I don't know, radiation coming in, which has a much higher temperature, right? And yeah, so I think that's the whole point. That if you want to use a qubit as a temperature sensor of something, you need to make sure that you couple it properly.
Yeah. Sure.
to other thing, because otherwise, what you will be measuring, you might be measuring something else. So if you have some other channels they are not very controlled, then that's exactly what would happen. You would expect that your excitation is 0, but in reality it's order of magnitude larger.
Sure. Yeah.
Yeah.
So this is like a calibration step. But if you had, say, some mesoscopic spintronics device or something where you have electrodes which have some temperature, or I don't know what kind of contraption you could think of. But if you thought that the electrodes were at a particular temperature, but you wanted to measure directly that temperature by coupling a qubit to the electrodes, I mean, is it feasible at the moment?
Yeah, that's actually what people. In fact, this is what we do now. Often,
Okay,
like
cool.
we have some components, right? And sometimes, like using qubit to certify that your component is thermalized, is actually the qubit is the best way to do it. So that's often is even done in a similar way. Yeah, that you kind of try to. Okay, maybe that's too bold to say so, but. Yeah, so but in principle, yeah, the idea would be exactly the same. So, for example, if you want to certify that your control electrodes have electron temperature, like low electrode, the best way to do it is to couple them to the qubit and see what the the qubit temperature.
Okay, I see. Yeah. Okay, thanks.
Do you have any references for that work, Arkady?
Okay, I mean, I have to think about it. Yeah.
Sure.
So,
yeah. So Kieran, I'm wondering. So the model that you've been using for looking at like the current generation, wondering. I mean, we'll look at the paper that might be a different like a viewpoint on how we could implement it, or whether we could model the implementation better with your model on.
Maybe.
Yeah, on your current your qubit with essentially. So Kieran's done a model with essentially like many qubits, and how it has sort of a a sync and a sort of like a sync and second source, so essentially a current from qubits. So it might work nicely with the work that's out there. But we'll have a quick read of whatever references that you can find. So I'm going to have to in the present the meeting there. This is one of those meetings where we could have talked for quite a while, but unfortunately it's backfiring for me. So yeah, thanks again, Arkady, and of course we'll continue talking.
Yeah.
Okay. So any other questions, comments? Okay, quick one, Seth. You're on mute. You're on mute.
When are you coming back? Are you available on Thursday?
It's just this one day. I'll be back in Melbourne next week.
Sure.
Tomorrow.
I will look at your calendar. All right, thanks.
Sure. Okay. Bye-bye, everybody.
Thank you,
See ya.
Arkady-san.
Thank you.
Thank you.
so much.
Thank you very
Thanks.
much.
Thank you.
See you sometimes in person.
There's